Hi children, how are you? I hope you are doing well. Today we are discussing important topic of moving charges and magnetism. A current loop as a magnetic dipole. A current loop means you can take a circular loop or a rectangular loop or a square loop in which the current is flowing, and that loops they behave like a magnetic dipole. That means they behave like similar to a magnet. For example, let me take a circular conductor. Current is flowing in a circular conductor, and that circular conductor will behave like a magnet. It behaves like a magnet. We'll call it as a magnetic dipole. Now, before going to the coming to our topic, let us discuss little bit electrostatics because I have to derive the formula for that also. Let us discuss in detail a little bit about electrostatics which is related to this. For example, if you take electric dipole, electric dipole you studied in electrostatics. A dipole is one which have two equal and opposite charges separated by certain distance. Let us say plus q and minus q are the two charges. They are separated by certain distance and connected by a massless rod. Imagine this is a massless rod. This is the center of the electric dipole. They are separated by certain distance, I said no. So let it be a plus a, 2a. So the two equal and opposite charges separated by certain distance. Now, do you remember we defined which is called dipole moment? Dipole moment we defined p bar. It's a vector quantity, and the dipole moment is given by its magnitude is given by charge into the distance between the charges. And it is a vector quantity, and its direction is always from minus to plus. This is the direction of p bar. I hope you remember this. One more point. The field. Now, electric dipole will have a field, electric field surrounding it. It will have a electric field surrounding it. Then I wanted to find the electric field on axial line. So, for example, okay. So, on axial line, I would like to determine the electric field. This is an axial line. This is called an axial line. So any distance on axial line or an equatorial line or any distance around this dipole is measured from center of the dipole. You know that. From here I have to measure the distance. Suppose I would like to determine the electric field at this point. The electric field at this point will be acting towards the negative charge because this is nearer to this. So this is the direction of electric field. So for a short dipole, short dipole means what? Say for example, this distance is r. That means you are determining the electric field due to the dipole at a distance r from center of the dipole. I said all distances are measured from center of the dipole only, no? So at this point, the electric field is given. Let us write the formula for that, especially for short dipole. Short dipole, what is the condition? And this distance r is very large compared to small a. Then you will call it as a short dipole. Then the electric field at this point is given by 1 by 4 pi epsilon naught into 2p divided by r cube. So this is an electric field on axial line at a distance r from center of the dipole, whose dipole moment is q into 2a. So this information is required for our discussion. Anyhow, it will be a small revision for you. I think you don't mind about that. Now let me take a bar magnet. Because I said that a current loop behaves like a magnetic dipole. So let us come to the magnet now and see how it is. And then we come to the dipole. So let me take a bar magnet here. Say this is a bar magnet. A bar magnet has a north pole and as well as south pole, like positive charge and negative charge. Two equal and opposite charges, no? So two equal and opposite poles. Let the pole strength is small m. Let the pole strength is small m. Remember one point if you come to the units. You know, this Q is measured in coulombs. Charge is measured in coulombs. Similarly, pole strength is measured in ampere meter. Ampere meter. That is the unit of pole strength. So Q resembles a small m here, and plus resembles north, minus resembles south. See, for example, two equal and opposite charges. So two equal and opposite poles. Equal means their pole strengths. So there is a lot of similarity here. They are separated by certain distance, you said. Let the distance is same, I'll take 2a. This is called magnetic dipole. This is called electric dipole. Bar magnet itself is a magnetic dipole. That's it. So let me determine the same. You'll have as a dipole moment here, electric dipole moment. You'll have a magnetic moment also. So magnetic moment is represented by capital M. Small m is pole strength, capital M is magnetic moment. Okay. And it is a vector quantity. And its magnitude is given by same. Charge into pole strength into distance between the charges, distance between the poles. That's it. And you said that M is measured in ampere meter. And 2A means it is a length. So it is also measured in meters. Ampere meter into meter. How much I get? Ampere meter square is the unit of this dipole moment. Here also, this is coulomb meter. Coulomb meter will be the unit of dipole moment. Electric dipole moment, magnetic dipole moment. And it is also vector quantity. It is directed from minus to plus. Minus to plus here, south to north here. This is the direction of M bar. Right. So what is present around this bar magnet? Magnetic field is present. I want to determine a magnetic field on an axial line of the bar magnet. As you measured here also all distances. Whether you take this point or this point or this point or this point. Any point you are measuring. The distance of the point you are measuring, you have to measure from center of the magnet. Now let this is an axial line of the bar magnet. This is an axial line of a bar magnet. Like this. Now at this point I would like to determine the magnetic field that is on axial line. So that let it be B axial, it will be towards the south pole here because south pole is nearer. B axial. At what point you are determining? At a distance R from center of the bar magnet. So from center of the bar magnet at a distance R magnetic field. A similar formula you are expecting. Definitely. B axial. 1 by 4 pi epsilon naught. So you will be getting mu naught by 4 pi. Here also we will take short dipole only. So short magnet. What is a short magnet? Same condition. Small r is very large. This r is very large compared to this a. I said no, this is a plus a, 2a. That is short magnet. For short magnet, at a distance r from the center of the bar magnet, the magnetic field on the axial line is given by. This is 2 capital M divided by r cube. Similar formula, you got it. But this is a magnetic field, that is electric field. This is electric dipole is producing electric field, magnetic dipole is producing magnetic field. So there is a lot of similarities. Now, I'll erase this part and I'll bring the current loop now. Let us see. So, one more point. Here, a magnetic field. How does a magnetic field look around this? See the magnetic field here and electric field here. If we take an electric field here, the electric field looks like this. Electric lines of force I am drawing. This is how the electric field looks. You might be knowing about all this. You're supposed to know, but if you don't know, it is a little bit difficult for you. So this is the direction of the lines of force. They see, all of you, this is how the electric field looks. The electric field looks like this around the electric dipole. You all know about electric lines of force or magnetic lines of force. The lines of force are here, which makes you to understand the electric field and also the direction of electric or magnetic field. If these lines of force are, more crowded, okay, there is some disturbance. Just a minute. So what you observe here, the electric field can be understood with the help of the lines of force. If the lines of force are more crowded, there the field is strong. And the tangent, if you want a direction of magnetic field at any point, you have to draw a tangent at that point. That gives the direction of magnetic field. Anyhow, you can understand electric or magnetic field with the help of lines of force. Let us see how are these lines of force now. This is a bar magnet. So this will be resembling that. Same. See, this is how the magnetic lines of force. These are called magnetic lines of force. They are known as electric lines of force. They are electric lines of force. So these are always, you can see one point, the magnetic lines of force are diverging from North Pole and converging at the South Pole. The electric lines of force are diverging from positive charge and converging at the negative charge. So the field also looks similar. Let us see now, I'll bring this current loop into the picture. Let me remove this electric dipole because our discussion is about magnetic field. This is only just to make you understand, because you have already studied about electrostatics. Maybe it will be helping you. That is why I took this dipole. Otherwise not necessary here for me. I require only magnet and current loop here. So let me take the current loop. So this current loop means for example, I can take a circular loop. The current is flowing like this. This is the radius of the loop. Let me take as radius of the loop as capital R, and on the axis at a distance x from center, what is the magnetic field? I want magnetic field here. I hope you remember I derived this expression for you in a previous lecture. So the magnetic field here will be towards this B axial, because towards this. So this B axial is given by, do you remember the formula for this? Due to a circular conductor having current at a distance x, the magnetic field on the axial line is given by, this is mu naught Ni r square divided by 2 into r square plus x square whole to the power of 3 by 2. This is the formula. I want to relate this. So what is my aim is, you have a magnetic moment here. There you have an electric dipole moment, P bar. Here capital M bar. So if this is behaving like a current loop, behaving like a magnet, then how does a field looks? What will be its magnetic moment? That is what I want to discuss, right? Now here also I will take x larger than radius. That means I will be taking a smaller loop like this. And at distance x I will be taking large. You will be finding the magnetic field here. So this radius is small compared to the x. So I should say x is very large compared to the radius. So take a smaller root and x you take little bit more larger, then x is large compared to the radius. That is called shorter. As you have taken short magnet, you have taken one condition here. Here also. Here r is the distance, here x is the distance. From center of the magnet, r is a distance. So from center of the circular loop, x is a distance. You said a is small. That means r is large compared to a. Similarly, x is compared large to the x is larger to the radius, much larger than radius. So there is a lot of similarity. Okay. Now in that case, I can neglect this r square. Some student asks, sir, neglect this r square also. See, r square is neglected when compared to x square, not independently. Suppose if x square value is 10,000, if r square value is 1, compared to 10,000, I can neglect 1. So 10,000 whole to the power of 3 by 2 or 10,000 plus 1 whole to the power of 3 by 2, almost nearly same. That is what I mean. Don't neglect here, understand? So then what happens to B axial? This B axial is equal to, this is mu naught n I r square divided by 2. Okay, r square is neglected, x square to the power of 3 by 2, you have 2 gets cancelled. So 2 times x cube. I want to bring these two formulas similar because both are magnetic fields only. You are calculating magnetic field here. Here also I am calculating magnetic field. Only difference is there you have a bar magnet, here I have a circular loop having current. That's the only difference. So I want to bring it to, so similar to this. So I do one thing here then. Because I have 4 pi here, I have only 2 here. I do one thing then. I'll multiply by 2 pi here and as well as 2 pi here. Fine. What will happen now? So 4 pi. So 2 2s are 4 pi. Got it. Mu naught by 4 pi here is there. Here also I'll get mu naught by 4 pi. So B axial is equal to mu naught by 4 pi. Yes. Then 2. Yeah, 2 pi is 2 pi into 2, 4 gone. The 2 is there. No problem. I'll write 2 also. Next. Divided by x cube divided by r cube. Good. R is a distance from center. Here x is a distance from center. Good. Then pi into r square. Pi into r square is area of this. That is area of this. So area NIA. This is the formula. I got it now. So now our exact discussion will start regarding this. The direction of magnetic field I want. Direction of magnetic field. So I will apply right hand thumb rule only. If this is a current carrying conductor, if this is a current direction, then these 4 fingers will give you the direction of magnetic field. I will do same thing. This is a current carrying conductor in this area. So magnetic field is inward. Inward. Let me check here also. Fine. Current is downward. So magnetic field is again inward. Let me check here if you want. Current is like this. Right? Because it's flowing like this. Then the magnetic field will be inward. Check here also like this. So current is flowing like this. Magnetic field inward. So magnetic field is always inward. So I will take an inward magnetic field here. I will take an inward magnetic field here. Now. So the magnetic field is going inward. So here also magnetic field is going inward. When it is going inward, what pole you have, Amma? Here, south pole. So here also you have a south pole. Then they are forming a loops. See, like this, like this, like this, like this, like this. So here also they must form a loops like this, like this, like this, like this, like this. So then other side you have what pole, Amma? North pole. So therefore, then if the magnetic lines of force coming like this, then other side, that is behind, you'll have a north pole. So I could see now exactly same, but this is a little bit thick. That means this length is more bar magnet, but this is a ring. That's all. But that is naturally a magnet, but there is no magnet here, but current loop is there. But even current loop is also producing magnetic field similar to this. So there is a lot of similarities. South pole here, south pole here. You have a converging field. I have a converging field. Then it will diverge from north pole. Yeah, it will diverge from north pole. That means the other side, behind you have a north pole. Next. Then if this is a magnet, this is also a magnet. Having south pole on one side and north pole on other side. When it has a dipole moment, then it will also have dipole moment. When it is having an axial field formula, even this also has an axial field formula here. So exactly same you are finding. So what will be the dipole moment if I compare these two? So here is the dipole moment, here is a dipole moment. Therefore, the dipole moment of this loop, okay, capital M, is equal to NIA. N is number of turns. Of course, in this formula, N is number of turns only, no? So the number of turns. If you have one turn, you substitute one only here, no problem. And current is I, and area of this loop is A. So this will be the magnetic moment. So bar magnet has a magnetic moment. And even this also magnetic moment. What are the units? Ampere meter square. Here also you will have the units ampere meter square only. Now our discussion is this. A current loop behaves as a magnetic dipole. North pole on behind, south pole in front. And its magnetic moment is NIA. This is our discussion. Now I can tell you one thing, one important point here. So this is a circular conductor like this. You have determined a magnetic field here. The current is in clockwise here, clockwise. See, observe one point here. When you have a current in clockwise, like this, you can see current in clockwise here. The current is in clockwise like this. So this diagram I kept like this. This is an axis. So current is in clockwise like this. What pole it is having? South pole. You can remember like this also. The ends of the S will match with the direction of the current. South pole. Now, if the current is in anti-clockwise direction, so that will be behaving, that phase will be behaving as the north pole. Here also the arrows will match. The tails put an arrow, then it will match with the direction of current. You can remember easily now, isn't it? No confusion. Now one point is very important. Many students will think that these two are different rings. No, that is same ring. See, if the current is clockwise, flowing like this, you will have a south pole here. Now for you, this is in clockwise. For me, it is an anti-clockwise. For me. Therefore, if you have a south pole here, then I will be having a north pole here. Therefore, this circular ring is behaving like a south pole on one side and north pole on other side. So similar to a magnet. And that is what you are discussing here. It has a magnetic moment also. And that is given by NIA. I can tell you this example more clearly with visualization. Let me take this paper. Now I have a circular loop here. Current is flowing like this. Oh, Okay, anti-clockwise. Let me take this. Okay. So then I have a north pole here, this phase, right? So for you, it is anti-clockwise current having north pole on your side. For me, it is looking clockwise because I am opposite to you. For me, it is looking clockwise. Shall I show you? See. Is it clockwise or not? Yes. Means what? One side, it will be seen as anti-clockwise current, north pole. Other side, one side, it is seen as anti-clockwise current having north pole. On other side, same conductor will be seen as clockwise current. Then this will behave like a south pole. This direction matches with the current. This direction matches with the current. Yes. So, therefore, for a circular conductor having current, one side will have a north pole and other side will have a south pole. And not only circular conductor, any loop. It can be, need not be a circle, it can be square, rectangle also. So one side will have a north pole, another side will have a south pole. And its magnetic moment can be calculated by NIA. That is our discussion. Let us do one or two applications on this. Okay. See, finding the magnetic moment NIA for a circular loop, etc. like that. So there is very simple one formula I derived for you, that is N into I into A is the magnetic moment of a current loop. N is number of turns, I is the current in the loop, A is the area of the loop. Now let me take one problem like this now. You have an x-axis here, you have a y-axis here, you have a z-axis here. This is a xz plane. This is an xz plane. If you take a room, one corner, this corner will be origin. Then this will be x-axis for me. And this will be y-axis for me. And that corner like this will be z-axis. The flooring is xz plane because this is x, that is z. So xz plane is flooring. What is wall? So you said this is x-axis, this is y-axis. So wall will be xy plane for me now. Same situation here also. The wall is xy plane. The flooring is xz plane. So I am taking one circular conductor here. Whose radius is r, current is I. Find the magnetic dipole moment. We have already decided it behaves like a magnet. So it will have a dipole moment. That is given by N into I into A. Fine, N is 1. Anyhow, because you have taken only one turn, so N will be 1. So the magnetic moment of this is N I A. This is N is 1, current is I, area is pi r square. But it's a vector. Its direction must be given. I will give simple method for determination of direction of this M bar. Let me tell you. Suppose if you have a circular conductor like this, you know this will behave like a north pole here, definitely north pole here. And behind you'll have a south pole. I want the direction of dipole moment. Direction of dipole moment is from south to north. So then what will happen? This is the situation. You have a north pole here. You have a south pole behind. Then south to north means it is like this. So this is the direction of dipole moment. South is behind. North is in front of you. So this will be the direction of south to north. Now suppose if I reverse this. Yeah. See, if this is a dipole moment like this. If I reverse this, dipole moment also will reverse. It will come towards me now. It was towards you. Now it will come towards me. Okay, let me reverse this conductor. Okay. Then this will be behaving like a south pole here. You know that. Like this. So here is a dipole moment like this. Then this will be the dipole moment into the board. So let us avoid this confusion. I'll tell you one rule. Let me use the right hand thumb rule. If this is the direction of current, 4 fingers, the thumb will be the direction of magnetic moment. That is easy method for you. So now the magnetic moment is outward. So M bar is outward now. here. Okay, check here. Here M bar is inward. Anyhow, M bar will be from south to north. So inward for south and outward for north. Always. So use this rule. What is the magnetic moment direction now? This is the XZ plane now. It is current is flowing like this. Like this. So this will be the direction. Along y-axis. Because this ring is on XY plane. Because this ring is on XZ plane like this. Then current is flowing like this. Like this. Then the direction of magnetic moment, this is direction of magnetic moment, is along y-axis. So I will give a direction now. Along y-axis means j cap I'll give you. J cap. So this is with vector form I gave answer. Vector form. So let me take another example. A current is flowing like this. I will take one current loop on XY plane now. So this is a current loop. The current is flowing like this. Let me take clockwise. Okay. This is A and this is B. Current is I. Find the magnetic moment of this current loop. Magnetic moment of this current loop. So magnetic moment is given by NIA. So therefore it is given by number of turns means only 1. I means I. Area of this rectangle is AB. Fine. Direction. Use right hand thumb rule only for direction. See, current is flowing like this. Clockwise. So it is inward. Inward. So how will you take direction of inward? I cap, J cap, K cap, minus I cap, minus J cap, minus K cap. Which one I should give? See, if this is x-axis, right? If this is y-axis, and z-axis will be like this towards you, right? So I am getting this direction in negative x direction. See, because if this is x, this is y, this is z. And into the board will be minus z. But I am getting this direction into the board. So along minus z axis. So I should take minus k cap here. M bar I will write now. After putting k cap, I can write M bar now. So this is the magnetic moment. Let me take one more. So x-axis. This is y-axis. And this is z-axis. Now I'll take current loop differently. This is the current loop. And this side is A, this side is B. Similarly, this is A, this is B. Like this, the current is flowing. So there are two loops here now. You may have, sir, one loop is on XY plane, one loop is on XZ plane. That means one loop is on the flooring and one loop is on the wall. You will get a doubt there is no completion here. I will explain you. Suppose if the current is I am asking. So I am asking to find the magnetic moment of this loop. So the magnetic moment of this loop I will calculate. See, let us assume there is no current here, but let us assume that current I is coming like this. Let us say if this current I flows here. Right. Similarly, this current is coming like this. Let us say this current goes like this here, I. So these two will nullify and current becomes 0. And that is why they are flowing like this. So these two opposite currents nullify. They cannot go. So therefore it will go like this and this will go like this. So I can have an imaginary current like this. both in clockwise and anti-clockwise. But as a result, the current will be 0. Now this can be taken as a closed loop. What is its magnetic moment? So let the magnetic moment of this system is m bar. Then this is magnetic momentum of the first one, magnetic moment of the first one. This is loop 1, this is loop 2. So this is m1, n into I into a. Of course n is 1, I means I. Area means AB. Direction we did just now here, minus k cap. Plus, now coming to m2. Again I into area means AB. Now direction. See, direction is now, it is like this. Current is like this. It is on XZ plane. So current is like this. Therefore, I will be getting down. I'll be getting down. So down means what? This is J cap you will get here, minus J cap I'll get here. So this is minus J cap. So finally, the magnetic moment m bar is equal to, so AB into I, common on both sides, bracket, I'll write minus J first, then I'll write minus K. This will be the magnetic moment of this loop in vector form. Like this, they may ask you to find the magnetic moments, etc. like this with the loops. So next topic is now current loop as a magnetic dipole. So these all are loops only. And in each case, you are finding the magnetic moment. Okay. But now the next one is, if a charge is revolving in a circular motion. For example, electron is revolving in a circular orbit. That can be considered as a circular loop having current. Then how will we calculate the magnetic moment of the orbit, okay, in which the electron is revolving? Let us see that. Now let us see, an electron is revolving in a circular orbit. An electron revolving in a circular orbit. Let us say the electron is moving with velocity v. You know, charge of the electron is represented by E minus. And let the radius is r. Electron revolves very fast like this. You know, velocity of electron is very large. So it will be revolving very fast. Therefore, you can assume there is a current in the orbit now. There is no conductor, but orbit will have a current. You know, definitely current is due to what? And the flow of charge. You know, rate of flow of charge is called current. So when electron is revolving, I can assume it's a flow of charge. At a particular point, if you observe now, suppose this is our observing point, then I see this electron is going so many times here, very, very fast like this. When it's revolving very fast like this, it's going so many times here in 1 second for me. So therefore, for me, it will be a flow of charge if I observe it at one point. Therefore, I can assume some current here now, like that every point. So if a charge is revolving, you all know that the current is nothing but the rate of flow of charge. Right? Say if the time period of the electron is capital T, then charge of the electron is E, then I can write it as E by T also. So you can also write this current as frequency into charge or frequency into charge. It need not be electron. It can be any other charged particle also. So always frequency into charge is the constitutes a current in that particular orbit. Anyhow, 1 by T is frequency only, no? Fine. How to understand this now? See, for me, if you are observing electron, suppose this is a starting point for me here. So electron goes around and comes here, and it will pass one time. When it passes one time, how much charge is passed for me here? E. After how much time? Capital T. So that is nothing but rate of flow of charge. Now this is equal to E divided by. So time period is time taken to complete one revolution. If time taken to complete one revolution, you know that time is distance by velocity. What is distance? 2 pi r. 2 pi r by velocity. Therefore, the current in the orbit is E into V by 2 pi r, or else Q into V by 2 pi r. If electron you write E, any other charged particle means you can write its charge Q also, no problem. So I got current in the orbit now. So if this orbit is behaving like a circular conductor now, there is no conductor, there is no current, but still electron is revolving like this, then this orbit is said to have a current. Then it behaves like a circular conductor only now. So it will have a north pole on one side and south pole on the other side, and it will have a magnetic moment also. So the magnetic moment of this orbit, the magnetic moment of the electron is given by I into A. Anyhow, N is taken as 1 here. So what is I? Here we have E into V divided by 2 pi r into area of this pi r square. Fine. Small r square. So pi is getting cancelled, small r is getting cancelled. Therefore, magnetic moment M is equal to EVR by 2. If it is some other charged particle, this is QVR by 2. This is a magnetic moment. Just a minute. This is a magnetic moment. Okay? This is a magnetic moment. This is a magnetic moment. Direction I want. Direction. Right? If electron is revolving like this, opposite to the direction of electron, you will take the current. Remember always. Direction of positive charge is required here. So therefore, the imaginary current is like this. That is opposite to the electron. Then you use the right hand thumb rule now. So inward. Magnetic moment is inward. So I can give the direction also for this. So therefore, the magnetic moment of a revolving electron is given by this. If other charged particle is given by this, where V is the velocity, R is the radius, E is the charge of the electron. Next, in most of the cases, they talk about the angular momentum of the electron. Even in the Bohr's theory also, they talk about angular momentum of the electron. We are going to discuss that one also now. So, if angular momentum of the electron, if it is represented by L, let us say angular momentum is represented by L. L. So, it is nothing but R bar cross P bar. Oh, here P is not the dipole moment of the electric dipole only, please. P is product of mass and velocity. That is momentum of the electron or momentum of the charged particle. So this is L bar is equal to R bar cross P bar. Anyhow, let us see where is R bar. See, here is R bar. This is R bar. Where is P bar? P bar is mass into velocity. So here I will take mass into velocity bar. So this is P bar. Where will be the direction of R bar cross B bar? So this is R bar. This is P bar. R bar cross P bar will be outward. That means R bar cross P bar will be like this. So R bar cross P bar, the direction of R bar cross P bar is nothing but direction of L bar. Yeah, this is R, this is P, R cross P will be outward now. So this is the direction. Anyhow, this radius and this momentum are perpendicular. So therefore the angular momentum is given by R into P into sine 90. A bar cross B bar is AB sine theta. So A means magnitude of R, P means MV I can take, theta is angle between L bar and P bar, which is 90 degrees. So this is nothing but M into V into R, because this momentum, okay, let me write this is R into M into V. This is the angular momentum of the electron. This is equation 1, this is equation 2. So for a revolving electron, this is angular momentum, this is magnetic moment. Magnetic moment. So this discussion will be there in most of the cases when you consider a charged particle is revolving. Now the ratio between these two I want. That is the magnetic moment divided by angular moment. Angular momentum of the electron. So here is a magnetic moment EVR. EVR by 2. The magnetic moment, angular momentum is L is given by M into V into R. M into V into R. Let me cancel this radius, this velocity. What do you have? The ratio between M and L, that is the magnetic moment of the electron to the angular momentum of the electron, is E divided by 2m. If it is not electron, some other charged particle, I can write Q divided by 2m. This is very, 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 very important relation. Very, very, very important relation. Either electron or any other charged particle, no problem. When it is revolving, so you can consider that orbit as a dipole. So dipole moment is given by this relation, and angular moment of that particle is given by this relation, angular momentum. The ratio between these two always equal to this. So again, the ratio between the angular momentum, magnetic moment and angular momentum is given by this. I want to apply Bohr's theory here regarding the angular momentum of the electron and check what happens in this case. Now if I take here Bohr's theory for like hydrogen like atoms, for hydrogen like atoms, for hydrogen like atoms, the angular momentum of the electron, here there already, is equal to an integral multiple of h by 2 pi. Angular momentum of the electron is equal to an integral multiple. N is equal to 1, 2, 3. H is Planck's constant. You know this relation. Now using this relation, I want to express the magnetic moment now. Let me take this relation. So the magnetic moment divided by angular momentum is equal to E divided by 2m. Then I'll send L to this side. So the magnetic moment of the electron now in hydrogen like atom is given by E by 2m into L. But what is L? N into H divided by 2 pi. Therefore the magnetic moment is given by, anything is cancelling, fine, otherwise you leave it off. N into E into H, 2 2s are 4 pi m. Remember here small m is mass of electron, H is Planck's constant, E is charge of electron, N is an integral multiple like 1, 2, 3, 4. Anyhow here N is a principal quantum number and capital M is a magnetic moment of electron. This is a relation. Now if the electron is in the first orbit, if electron is in the first orbit, if electron is in the first orbit, N is equal to 1 I'll take. Therefore the magnetic moment is given by E into H divided by 4 pi m. So if you substitute this one as 1.602 into 10 to the power of minus 19 as a charge of electron, 6.6 into 10 to the power of minus 34 as a Planck's constant, 4 into 3.14, that is pi value. Mass of the electron, I'll take 9.1 into 10 to the power of minus 31 kgs. And it is measured in ampere meter square. The unit of this magnetic moment is ampere meter square. So now if you simplify this, you will be getting it as 9.27 into 10 to the power of minus 24. You will get, on simplifying, ampere meter square. This will be the magnetic moment of the electron in hydrogen-like atoms in the first orbit. This is called Bohr's magneton. This is known as Bohr's magneton. This value is called Bohr's magneton. Now, next part is that, the last one. You will be taking a ring, a charged ring, and that ring will be revolving with certain angular velocity. Then you will be proving the relation, the ratio between the magnetic moment and the angular momentum is equal to Q by 2m. See, the ratio between the magnetic moment by angular momentum is Q by 2m. I want to verify. I will take a charged ring now. This is a ring. A charge is given on the ring. Mass of the ring is, there are so many m here. Okay, mass of the ring is, I'll take m dash. No confusion. M dash is mass of the ring. R is the radius of the ring. Now this is the axis of rotation. The ring is being rotated with an angular velocity omega. Now I have to prove this. I have to prove this relation now. The ratio between the magnetic moment and angular momentum. Where is magnetic moment? Where is current? Where is... you have to understand that fast. See, this loop having charge Q, not current. There is no current in this circular conductor now. Or this circular, not conductor, circular loop. Or I say, we have to take a non-conducting circular loop. I have to take. Then you are giving a charge on this loop. No current. Fine. Now when this loop is revolving, then it can be imagined like a circular conductor having current. How? Suppose when this is revolving like this, take one point of observation. You are observing here. When a ring completes one revolution, how much charge will pass here? Q. Because Q is distributed on the ring. So when ring completes one revolution, charge Q will pass from point of reference. So therefore, how much charge is passed? Q. After one revolution, the time taken for revolution is T. Therefore, the imaginary current in this ring can be taken as Q by capital T. So this is nothing but here don't try to solve like in previous case. Omega is given here. So the angular velocity is equal to angular displacement by time. So for one revolution, it will cover an angle of 2 pi radians in a time t. Then angular velocity of the ring can be written like this. Therefore, what will be t here now? 2 pi by omega. Now I'll substitute that here. So therefore, this is nothing but Q divided by capital T is nothing but 2 pi by omega. This is an imaginary current. There is no current. Because it is revolving, I can have an imaginary current like this in this circular ring. So when you have an imaginary current in the circular ring, it will have its magnetic moment. That is I into A. So I is this. I is this. And A is nothing but pi r square area. So this pi gets cancelled, right? Anything else? That's all, no? Q into omega by 2 pi, that is I pi r square, right? Therefore, the magnetic moment of this ring, which is behaving like having an imaginary current, will be equal to Q omega r square by 2. So, magnetic moment is over now. Next, I will take angular momentum now. What is angular momentum of the ring? The angular momentum is always given by moment of inertia into omega. So therefore, this is given by moment of inertia. Formula is mr square, where m is mass. Omega. For ring, moment of inertia is mr square. Omega. So this is equation 2. I want the ratio between m and l now. Okay? I want the ratio between m and l. Oh, so many calls are coming. So this is m divided by l is equal to Q into omega into r square divided by 2 divided by m dash into r square omega. Therefore, the ratio between m and l is equal to, I cancel one r square, I cancel omega, this is q divided by 2 times m dash, where m dash is the mass of the ring and q is a charge. The ratio between the angular moment and the ratio between the magnetic moment and angular momentum is q by 2m or 2m dash, where m is the mass. So I have proved in the case of rotating ring also. You can also prove if the charge is distributed on a sphere, on a circular plate. In all these cases, the ratio between the magnetic moment to the angular momentum is always equal to q by 2 times the mass. In other cases also you can prove. So this is very, very important information. Okay, thank you.